So for our next example, we have this problem here. And in this case, notice that they've given us the expressions that they want us to use. And these expressions are both for time is greater than 0. So what is happening? Firstly, we want to understand that for an inductor in a source-free circuit, and you can see that this is source-free, we don't have a power source here. So here, for an inductor in a source-free circuit, the natural response from the inductor is in form of current. So you have I, function of time, will be the initial current in the inductor at t is equals to 0, multiplying the exponent of e to the minus t over the time constant. So this is the shape of the natural response from an inductor when it is in a source-free circuit. So with that in mind, look at what that implies. Firstly, we have this. Find the total resistance R, or find the value of A, which is the total resistance R, so which is going to be the value here. And then find the time constant tau. And then finally, find the inductance L. So when you look at the values they've given us here, clearly for an inductor, we note that the natural response is not in terms of this. The one we derived is in form of current. And since this expression does not just say what the current is at a specific time, it actually defines the expression, it tells us what the current is at any time t greater than 0, meaning that this was actually describing the natural response from the inductor, implying that when we compare the two expressions, you should be able to see that where we have the initial current from the inductor, we have 5. So here we can see, of course, you just want to observe that this is in milliamps. So this is in milliamps, meaning that even when we get our I0 there, when you get it as 5, you should recall that, or you should see that this 5 is in milliamps. Next, we have the expressions on top. We know to say it is minus t over tau, which is the power there, minus e minus t over tau. So when I try to extract the tau from that expression, how do I do that? So I can easily just say that, okay, from the comparison we have here, it follows that somewhere here, the minus 10 to the power 3t, since we had e to the minus t over tau, somehow this is the one that reduced to become e to the minus 10 to the power 3t. Or I can just say that this minus t over tau is the one that becomes minus 10 to the power 3t. Now I'm just solving for t. Or since in each case I have coefficient t, I can follow to say that somehow this e to the power minus t over tau, I can look at it as e to the minus, then I have 1 over tau multiplying t. So that here I can see the same thing, minus outside, then 10 to the power 3 multiplying t afterwards. What I'm trying to show here is that the 10 to the power 3 is what actually becomes equal to the 1 over tau. So you could have found it using any of these methods I've demonstrated there. So let's add more pages here. So, okay, so here we end up with, our expression should reduce to just having 1 over tau being equals to 10 to the power 3. So from here, we just now have to simplify this to find what tau is. Now that's 10 to the power 3. When we cross multiply, we see that 1 over 10 comes here, and then tau comes this side. So our time constant has reduced to just 1 over 10 to the power 3, or 10 to the power minus 3 when we use indices. And remember, when the time constant is used in this expression, it comes with units of seconds. So here, this must have had standard units, so we'll give it the units of the seconds there as the time constant. So once the time constant is sorted out so far, we have figured out just what the time constant is. We still have to get what R is. So to get R, we can use the values, the expressions they've given us, Vt and It. So how do we do that? Well, in this case, notice that for this expression, the current I is coming from the inductor and it goes this side. And Vt, we can look at it as the voltage being dropped. Of course, these are in parallel. So whatever the voltage is applied here must be dropped across that resistor. The resistor obeys Ohm's law. So for the resistor, you have the voltage is equals to IR. So here, by using the voltage and the current, we can see that the resistance will be equals to the voltage over the current. So since they gave us the expression for the voltage, 80 e to the minus 10 power 3t, and then that's the voltage. And the current, we have 5 e to the minus 10, and then we have power 3t. Just don't forget the units, they affect what is happening. So we get this. With the expression for the current and the voltage, we can easily use those in Ohm's law to obtain what the resistance is going to be. So here, we now have R is equals to, for the voltage, we have 80 e to the minus 10 to the power 3t. The units are okay, standard units, the volts, but down here we have 5 e to the minus 10 to the power 3t, but the units here are the milliamps. So milli just implies times 10 to the power minus 3 amps. So now that I've converted, I've introduced the minus 10 to the power negative 3, might as well drop the milli, the amp, because I now know that even the current down there is in standard units. Well, here, of course, it's not just a matter of simplifying this. So what are we going to have here? Yeah, we can do this in so many ways. But the 10, we can sort that one out. Let's see what is common here. We see that the exponent, e to the minus 10 to the third, with a t there, it's common in the numerator, in the denominator. So this is going to cancel out, so that our resistance reduces to 80 over 5 by 10 to the power minus 3. So this is what we're now simplifying. 5 will go once into 8, leaving a 3, and into 30, it will go 6 times. So we have 36 there, is it? That's where did I get that 3, the first 3? So it will go once, and then leaving a 3, and into 30, it will go 6 times. So we now have 16 over 10 to the minus 3. 10 to the minus 3, when the 10 goes up, we now have 16 by 10. When it goes up, the negative becomes a positive this time. So this is what we have. And 10 to the power 3 is the same as a kilo. This was supposed to be in ohms, but with the 10 to the power 3, we can present this as 16 kilo ohms. So this becomes the value of R. So look at this, we have the value of R. Earlier on, we saw the value of the time constant. Now what we have, the time constant, we had 10 to the minus 3. In the other part of the same question, so we have L here, find the inductance. For an inductor, we know to say there's a connection between the time constant and the resistance. So the time constant will be equal to the inductance over the total resistance in the circuit. Had it been a capacitor, would have said the time constant is equals to the capacitance multiplying the resistor, had it been a capacitor. But in this case, we're dealing with an inductor. This is how the inductance and the resistance, they will relate. Since we already have the time constant and the resistance, we can easily get the inductance. Cross multiply here, you have L is equals to the time constant multiplying R. The time constant was 10 to the minus 3. the resistance was 16 kilo ohms, so you can present it as 16,000 ohms. The 10 to the power minus 3 will cancel the 3 zeros, so that the inductance comes out as 16. Now the question is, what will be the units here? So here, of course, this will be in henries. So here's what we did to get L. So we observed that for our circuit, what we have is a source-free RL circuit, as in it has an inductor. And we saw when we were introducing the concepts to say that if it is an inductor, the time constant was presented as the inductance over the overall resistance in the circuit, R. So this is what we saw when we introduced the source-free circuits. So since we had found the overall resistance in the circuit as 16 kilo ohms, and we had also obtained earlier what the time constant was, so it was now just a matter of plugging them in the expression tau is equals to L over R, making L the subject, reduced to L is equals to the time constant multiplying R. The time constant was 10 to the minus 3. R was 16,000 ohms. So, of course, we presented it in kilo, converting it back to ohms, it will have those 3 extra zeros. When you multiply this, the 10 to the minus 3 will cancel the 3 zeros, leaving the final solution as 16. Since we're going for the inductance, the units for inductance are the henries. So this is what we did here. In the second part, we now want to find the energy dissipated by the resistor during that period. So for t, for 0 less than the time, which is less than 0.5 milliseconds. So during this time interval, how much energy was dissipated? So of course, we still want to keep in mind what the voltage is. Vt is equals to 80 e to the minus 10 to the 3t. This is in volts, and it, we have 5e to the minus 10, 3t there, milliamps. Okay, so how do we work it out from here? So how do we get energy dissipated? Energy dissipated will relate to the work done. So we know to say power is equals to the amount of work done with respect to time, or how fast the work is being done. So here we end up with this is equals to power dt. And then finally, work done, which is equals to the energy dissipated, will be equal to the time integral of power times dt. So all we need is to know power. But in a circuit, we know to say power is equals to current times voltage. But they did give us what the current and the voltage, what they are. So just get these expressions, and we have to multiply them. So we have this. Okay, so this, the voltage, will multiply the current to give us the power. So just want to simplify this a little bit. The milli will make this the milliwatt. The volt and the amps will give us a watt. 5 will multiply 8 to give us 40. With that already existing 0 to give us this. Now we're multiplying e to the minus 3t, e to the minus 10 to the power 3t, multiplying e. So we see that this is the same thing we're multiplying. So when you're multiplying e to the power x, multiplying e to the power x, same base, add the powers. So this becomes e to the power x plus x, which will just be 2 times x. And so in this case, I just have to double that common power that the e carries. So this will be e to the power 2 times, to be negative, they're both negative, so it would be negative 2, multiplying whatever this 10 to the power 3 is. Then of course we have t here. This will be in milliwatts. So we now have the expression for power. In fact, if you're not comfortable with this, you can just power the 10 there so that it becomes 10 to the power 3. That would be 1,000. So that would just be 2 times 1,000. You end up with power is equals to this. E to the minus 1,000 by 2, you get 2,000 T in milliwatts. With the power obtained, we can now take it to the expression for work done. And work done, which is equivalent to the energy dissipated, the power for 400. So we plug in our power here, minus 2,000 T. Just remember, this is in milliwatts. So even though we have to, we have to integrate. Since this is coming with milli, when we integrate the power with respect to time, we are supposed to get work done. And the work done is coming in joules. But because of the milli which was present here, the energy when it comes out, it won't be in joules, it will be in millijoules. So let's get the integral there. Just for, we have the limits here. We know this is going to give us the energy dissipated, and the problem did specify the time interval. This was from 0 to 0.5 milliseconds. So this is from 0 to 0.5 milliseconds. So they didn't say whether there was something when we were starting at t is equals to 0. So we will assume that initially there was nothing which was happening there, so we are adding nothing there. So we won't really consider that additional that usually goes on. We'll just deal with the limits here. The part where we add mostly comes in when we're talking about current and charge. They'll say that, okay, maybe at t is equals to 0, there was some already existing charge. So that charge will have to be considered this side. But in this case, nothing has been mentioned, so we'll assume there's nothing was dissipated at first. So that we've just focused on what was happening in this window. So when you perform the integral, here we have an exponent. We know to say when integrating an exponent, all you have to do is differentiate the power. When you differentiate the power, you get minus 2,000. So we'll get minus 2,000. So here we'll have 400 here to remain the same, but the minus 2,000 will have to be divided here. And then the exponent itself remains the same. So this is how we integrate an exponent. Then this is from 0 to 0.5 milliseconds. So here, of course, the 2 zeros will fall with 2 zeros there. 4 will go 5 times into 20. So to now have 1 over 5 negative here. And then e to the minus 2,000 t. So 2 zeros fell 4, yes, we have that. So this is from 0 to 0.5 milliseconds. So when substituting, remember, when I get this was supposed to be in joules, but because my power was in milliwatts, I know this will be in millijoules when I get it. So I'll just keep that in mind. So in substituting for time, I know standard for time is supposed to be the seconds. So I'll convert this to seconds so that, of course, the milli just means 10 to the minus 3. So this is going to be 0.5 by 10 to the minus 3 when I take it to seconds. When I substitute the upper limit, what do I have? I can keep the minus 1 over 5 outside. When I put the upper limit, I have e to the minus 2,000 multiplying 0.5 times 10 to the minus 3. When I substitute the lower limit, I have to subtract. It will be e. The lower limit is 0, which will make the whole power to be 0. And this must be in millijoules. E to the power 0 is just 1, so I'm just focusing on the first part there, minus 1 over 5. 0.5 times 2,000, that will be minus 1,000. Then minus 1,000 is multiplying 10 to the minus 3. 10 to the minus 3 will cancel altogether. No, yeah, 10 to the minus 3 will cancel the 1000. So when it cancels the 1000, we now have minus 1 over 5. This remains as e to the power 1 minus 1 millijoules. When I distribute the minus 1 over 5, I now have negative 1 over 5 e plus 1 over 5. So this becomes the energy dissipated.